Since Newton method looks at quadratic approximations, so let's take a quadratic function to begin with. So consider a quadratic function. This could be of the form C transpose X plus half X transpose G of X, where G is the Hessian. And for quadratic functions, G is constant regardless of what X you pick. So for you can verify this very easily, that G k plus 1 can actually be written as gk plus the Hessian times the step length. Okay, and one way to see it is that gk minus 1, gk plus 1 minus gk is the difference in gradients is equal to the Hessian times xk plus 1 minus xk. Okay, so Hessian times the change in the coordinates. So this is really the definition of Hessian. It measures the rate of change of the first derivatives. For quadratic functions, this relation is exact. For other nonlinear functions, this is just an approximation. Okay, so using the terminology or the notation that we wrote earlier, this difference is our gamma. So gamma k is equal to gk times delta k. So in quasi-Newton methods, for general functions also, we want, okay, so this is a desirable property that we want from our hk. Remember that we are free to choose hk. So I'm going to choose hk so that hk plus 1 times gamma k is equal to delta k. Okay, so this is an important condition. So we would give it a name, quasi-Newton condition. Okay, and the motivation that we want H to satisfy this relation comes from the approximation to the quadratic functions, like we just wrote above. Okay, and from this it should be very clear that we can't choose hk here, because this delta and gamma are actually decided after we pick hk. So go back to the algorithm where we have to first set hk, then we choose a direction s and the step length alpha, which determines delta. And once we know delta, then we visit the new point and compute gamma. So once delta and gamma are known, only then I can find the next h which would be hk plus 1. Okay. So that is why hk1 is an approximation to gk inverse. Okay, so this this condition is important. We would like the choice of h to satisfy these conditions. Okay. So remember that this is an n cross 1 vector, this is an n cross 1 vector, and h is n cross n. So if I want to pick an h which satisfies these relations, then I can pick h in a huge number of ways. Okay, because the number of unknowns here is too many, but the number of restrictions are too few. So we also want, so this is a desirable condition. We also want hk plus 1 be positive definite. Even when we impose this additional condition, there could be many h's to choose from. So we can try to impose even more conditions on h so that we can find them easily. So the simplest condition is how to choose appropriate h. So we will discuss two methods today for choosing h. First method is what the book calls the rank 1 method. Okay. The rank 1 method this is not the actual name of the method, but Fletcher calls it the rank 1 method, and it was simultaneously discovered by several people. Which is quite a norm for these nonlinear type of methods, because several people were working in 1960s and 70s and 80s on these methods, and they were very popular topics of research, and the means of communication back then were not as fast as they are today. So there was independently the same methods were discovered by several researchers almost simultaneously in the same year or in a gap of 1 year or 2 years. So this rank 1 method imposes an additional condition on h, which is that the matrix hk plus 1 should differ from hk by only a rank 1 matrix. Okay, so what this says is, in addition to the above conditions, so additional restriction on hk plus 1 is hk plus 1 should be hk plus a rank 1 matrix of the form A U transpose. Okay, where A is a scalar and U is an n cross 1 vector. So you can verify easily that this would be an n cross n matrix, and U transpose will be of this form. First entry would be U1 square, and then we would have if I expand this would be U2 times U1, U3 times U1, UN times U1, and you can see that each column of this matrix is a multiple of the first column. So that means the rank of this matrix is going to be 1. Okay. So that is why this method is called a rank 1 method. So if I restrict my update in H to be rank 1 matrix with some scalar, I still have to decide what A and U can be. So what could be A and U? Okay. So it might be confusing to think that earlier we had to decide only H. Now instead of H we have to decide 2 parameters A and U. But note that U is only an n cross 1 vector and A is a scalar. So I really have to decide only n plus 1 values. And it turns out that if I restrict my updates to be of this form, then this AUU term is actually uniquely defined, and we are left with no choice really. So let's derive what could this be. So if I put this in the Quasi-Newton condition, which said that hk plus 1 into gamma k should be equal to delta k. So this implies hk gamma k plus a u transpose gamma k should be equal to delta k. So this implies that A U transpose gamma k should be equal to delta k minus hk into gamma k, and if we notice that this term is actually a scalar because this is 1 cross n and this is n cross 1, so this is a scalar, but this side is a vector. So that means this u vector should be parallel to this vector. So implies u must be parallel hk into gamma k. Okay. In fact, since a is a scaling factor which is under our control, I can pick u to be exactly this. Right. So pick u to be delta k minus hk gamma k. And if you put this value of u in this expression above, then we get a u transpose equal to delta minus h gamma delta minus h gamma transpose upon delta minus h gamma transpose gamma. So one thing about quasi-Newton methods is that we will see many terms like this where a vector is multiplied by its transpose, and also a vector being multiplied by a vector. So this is really a scalar in the denominator. This is 1 cross 1 matrix, and this is an n cross n matrix. Okay, so be careful about the dimensions, and also be careful in writing these expressions, because it's very easy to by mistake write delta in terms of gamma and gamma in terms of delta. So be a little careful here. So then the method becomes hk plus 1 is equal to hk plus this term. Okay, and this term is not that difficult to compute, because in every iteration we are anyway computing h. So this h, these are all previous iterates of delta h and gamma. The book avoids writing k altogether because it is tedious and creates confusion. So this way of updating hk gives us the rank 1 quasi-Newton method. Okay, so now to verify that this will actually work, recollect that we have to prove that hk plus 1 is going to be positive definite, provided hk is positive definite. Right? So we need to show that hk plus 1 is positive definite this is unfortunately not always true. Okay, so that means that the search direction that we will get in the next iterate may not be a descent direction. Okay. Also, it may happen that this method may have numerical difficulties when the denominator delta k minus hk gamma k transpose gamma k is close to 0. Okay. So even if hk is positive definite, if this denominator becomes negative, then this matrix may become negative definite, and this whole thing may become indefinite or negative definite. So so there are difficulties with this method. Okay. And you can show it easily that it is the numerator, which is an n cross n matrix, is positive definite. Okay. You just have to use the you just have to use the definition of positive definite, which is you take any x and do x transpose this matrix times x, and that would turn out to be a square matrix. So this is positive semi-definite actually. Not definite. So so if I add it to a positive definite matrix, I will get a positive definite matrix, provided this denominator is positive. If this denominator is close to 0 or negative, then we might run into problems, which might happen occasionally. So so this method is not really very useful, and the book actually says that this method was proposed after some rank 2 update methods.